Spectroscopy has to do with light and the interaction of light with matter and how much light is being absorbed or transmitted. If we take the amount of light that comes out and divide it by the amount of light we sent in, we get what is known as transmittance. If we multiply that fraction by 100%, we get what is known as the percent transmittance. And you often hear people talk in spectroscopy about percent transmittance. On the other hand, that's the amount of light going through the sample. We're actually more interested in the amount of light that is being stopped. The amount of light being stopped, that is absorbed by the material in the solution, is known as the absorbance. Absorbance is defined as the log of the light in divided by the light coming out. In other words, it is the log of 1 over the transmittance of the sample. Beer's law says the absorbance of the sample depends on 3 things. 1, the extinction coefficient of the thing absorbing the light. The better it is at absorbing the light, the higher its extinction coefficient. Second, L, the path length. Through how much of the solution does the light have to pass? And finally, C, the concentration of the absorbing species in solution. So, you can tell the concentration of a species in solution by simply measuring how much light comes in and out and getting the absorbance. And for that, you can get concentration if you know the path length and the extinction coefficient of the species you are looking at. In today's experiment, we're going to be trying to find out what the concentration of iron plus 3 is in an unknown solution that contains iron plus 3. Now, iron plus 3 in solution all by itself is a very pale yellow. That is, it has a very low extinction coefficient. And so in that case, the experiment wouldn't be particularly sensitive due to the low absorbance of the iron plus 3. The way we're going to get around this is we're going to add a solution of ammonium thiocyanate to the solution. In aqueous solution, the iron will latch on to 6 of the anions of the thiocyanate and form a metal complex, the iron hexacyanosinate. The nice thing about this compound is it is intensely dark red in color, as opposed to the very pale yellow that the iron plus 3 is all by itself. And so it is the absorbance of this species, the dark red iron complex, that we are actually going to be looking at. What we're going to do is we're going to make several solutions in which we know the concentration of iron plus 3, add the ammonium thiocyanate to it, and then take the absorbance of those solutions. We'll then plot concentration of iron plus 3 versus absorbance for those solutions. And we'll get a set of data that looks like this. We can then draw a straight line through our data points and the origin, and the slope of this line will simply be equal to the extinction coefficient times the path length. And so we'll now have epsilon L for doing our calculation. Then, using this graph, we can take the absorbance of our unknown solution and see where it falls on the slope of our line, and from that we can deduce what the concentration of iron plus 3 is in our unknown solution, thus finishing the experiment. What we have here is a spectrophotometer. This one happens to be in what is known as a Spec 20D. And it has several parts. On the top left side, we have the screen. The screen reads wavelength the spectrometer is looking at in nanometers. So this one is presently looking at the wavelength of 426 nanometers. Next to it, we have the instrument reading. This is reading either absorbance or transmittance, depending on what mode the spectrometer is in. On the right side of the deck, we have the control for the wavelength. Turning this knob changes what wavelength the instrument is looking at. Down in front, we have the two adjustment knobs. The 0 adjust for when there is no light going through the instrument, and the 100% adjust for 100% of the light is passing through the instrument. In the left top of the deck, we have the sample chamber. And what we use in the sample chamber is one of these. This is known as a cuvette. It looks like a test tube, but in actuality it's very specially designed and constructed to be optically clear. That is, there isn't any distortions in it that will affect the amount of light passing through. And that's the equipment we're going to be using today. We now need to prepare our sample solutions. Into our volumetric flask, we first add the ammonium thiocyanate, and our nitric acid. Stir them thoroughly. And now we have to add 2 milliliters of our iron solution from the pipette, from the burette rather. And as you can see, we're getting the dark red color of the iron thiocyanate solution. We now have to finish filling the volumetric up to the mark with deionized water. We filled it to the mark. Now we have to stir our solution thoroughly. And there is our first test solution. In order to use the instrument, we have to make several adjustments. The first obvious one we've already made is we set it to the wavelength we want, 430. Next, we have to tell the sensor what to be expecting. And the first step in doing that is we have to adjust the 0 adjust knob so that the reading is 0. This takes into account any stray light that might just happen to be inside the instrument affecting the sensor. We're telling it to ignore that stray light. We now have to set the 100%. And we could take our cuvette, fill it full of deionized water, put it in, and set the adjustment to 100%, because that's the amount of light that should be coming through a solution of pure water. And that would be fine if our solution contained just the iron plus 3 ions. But the fact is there are several other things in that solution which might be affecting our reading. That is, that might have some small absorbance themselves. So we have made the same solution as we're going to use in the test solutions, but we've made it without the iron plus 3 in it. And now we'll see what reading that gives. As you can see, the reading from our test solution itself without the iron in it is in fact a little less than that of the distilled water. This is why when you are setting up an instrument, you use a blank. That is, you use a solution that contains everything except the color species to see if those other things have some small absorbances. And so we are going to set our 100 not to distilled water, but to the solutions, the test solutions without the iron in them, so that we get a reading of just the iron's absorbance, not everything else that's in the solution. So now we're ready to take our first reading. And just make sure the 0 is reading 0. Put our blank in. Make sure we're getting a reading of 100. And now we can put our first sample in. And that's transmittance. We're not interested in transmittance for our samples. We want to get absorbance. So we have to switch the instrument to absorbance. And there's the reading for the first of our iron plus 3 solutions. We're now ready to take a reading on our second sample. We're checking that our 0 is still 0. That our 100% is reading 100%. Put in our sample, shift to absorbance, and there's the absorbance reading for our second test sample. So now we're ready to test our third sample. Again, I want to make sure a 0 is good. Check that our 100 is still reading 100. Put our third sample in, switch to absorbance. And there's the reading for our third iron sample. We're now ready to check our fourth sample. Again, make sure our 0 is 0. Make sure our blank is reading 100. Put in our sample and go to absorbance. And so there is the absorbance of our fourth iron sample. And finally, we're ready to take the reading on our fifth final sample. Again, our 0 reads 0. Put in our blank. 100 is reading 100. Switch to absorbance. And there's the absorbance of our fifth iron sample. And finally, we're doing our unknown. Our 0 is still 0. Our blank is still reading 100. And there is the reading for our unknown iron plus 3 solution.